Okay, coming back after giving you some time to do a paper-based exploration of dilation. Hopefully you've completed the activity. So there's a 3, 4, 5 triangle. We've dilated it together by choosing a center outside of ABC in the first example, and then we dilated it using different centers of placements of the center of dilation inside ABC, at a vertex, and on a side of ABC. So I'll show you what I'm getting, and hopefully you're getting something similar. So when I complete the activity, let me zoom in just a little bit. So there we go. So when I choose the center of dilation inside of ABC, the process is still the same. To get A prime, what I do is I march over 2 up 2, so I must have to double that distance if I'm scale factoring by 2 over 2 up 2, and there it is. A goes to A prime, and of course down 1 over 2, so down 1 over 2 there's B prime, down 1 over 2 there's C, so down 2 over 4 there's C prime. And interestingly enough, what I get is I get a triangle outside, kind of containing, enveloping the original triangle. If I change now down to this situation, this scenario, I chose A to be the point where I put D3 at a vertex. Of course, you could have chosen B or C. But what we get here is, of course, some sort of a enlargement of ABC where A doesn't change, right? Where, literally A and A prime. I mean, if I go, and probably should say that, if I go from A, D3 to A, you move 0, so scaling that by a factor of 2 is still moving 0. So A and A prime and D3 are all coincident, same point. But B, of course, down 3 becomes down 6, and C, of course, down 3 over 4 go down another 3 and over another 4. So we get kind of this nested triangle sort of scenario when a vertex is chosen. And then the last case was what happens if you choose a side. I chose the side BC and put D4 there. And of course, B and C just sort of move out. You're 2 units to C, so you double that, 4 units to C prime. Same for B. A is a little bit more difficult, but over 2 up 3, over 2 up 3 to repeat it, double that dilation. So I guess the big question is sort of what things do you notice, what properties seem to be evident. The first thing that should be pretty evident is that the center of dilation, a point, and its image are collinear. We saw that really here in this first one. And of course that makes perfect sense, right? If we construct the dilation by just doubling the distance from D to C prime in the same direction, you can kind of think of it like slope here. That slope is just repeated, at least for a scale factor of 2, it's repeated. If the scale factor is different than 2, the question is, well, take that distance and either, repeat it by a certain portion, I guess, of each of those distances. So definitely interesting, collinearity. We could find that collinearity here by just, drawing in lightly these lines, I guess, of collinear. Connect a point and its image, and of course these lines are already drawn in down here on this lower left hand, and the only one really to draw in here would be this one, A and A prime collinear. So point and its image and the center of dilation are collinear, probably best seen right here. Another thing that's kind of interesting to notice is that a segment and its image, you've seen this here, segment and image, they're always parallel under dilation. So segment and its image, segment and its image, segment and its image, always parallel. So here you can see this is parallel to that. A segment and its image parallel. These ones happen to be parallel and coincident. Parallel and coincident. Same thing here, parallel and coincident lines. But a segment and its image, segment and its image parallel. So some interesting properties. And then of course the one thing that we would automatically see as really different than the isometric setting is that a figure and its image are no longer congruent, right? So no longer isometric, meaning same measure, but they still look the same. In other words, they appear to have exactly the same shape. So this, of course, we call similar. So dilation is intimately related to similarity, because under dilation, an image and pre-image and an image, so pre-image and image are similar. That is, they're the same shape. All right. Looks like I froze up there a little bit, but I'm just going to let that go. So here's the definition of dilation. It's a dilation with center D and scale factor R. So you need two things. You need a center and a scale factor. It's a transformation of from the plane to itself that pairs each point A with a new point A prime in such a way that the center A and A prime are collinear, just what we found. And the distance from D to A prime is equal to R times the distance from D to A. So we just apply the scale factor to that distance from D to A, and that tells us where to put A prime. So what are some properties? Under dilation, the image and pre-image are similar. That is, corresponding angles are congruent and corresponding sides are in a common proportion. And then we also see that corresponding segments are parallel. So AB is parallel to A prime B prime, AC is parallel to AC prime, A prime C prime, and BC would be parallel to B prime C prime. So just what we found in the pen and paper exploration is true here as a property. So let's switch over now in this last piece and take a look at how we can use GeoGebra to support, I guess, understanding and viewing all the different ways that we can manipulate and understand reflection, rotation, and translation. So what I'm going to do is I'm going to give you three worksheets that you can just download and play around with in your own GeoGebra copy on your desktop. And you're certainly welcome to use these in your teaching if they would ever be helpful. But I obviously enjoy GeoGebra, and transformation is one of these places where, man, you can really make some beautiful pictures that allow kids to understand these transformations in a deeper sense than just looking at a static picture on a page. So let's take a look at reflection first, then rotation and translation. And then what I'm going to do, and I'll just go to the next slide, is I'm going to end by building, showing you how to build a GeoGebra file that dynamically demonstrates dilation and its property. And I will say that building something similar to this is the GeoGebra assignment for the week, so you'll want to pay special attention to this last piece. Okay, so I already have them open down here. Let's go to reflection first. So here's what I thought would be neat in reflection, is to build something that dynamically, when I grab one of these points, the other one responds. And I don't know if you feel that as pretty powerful, but I feel that as very powerful demonstration. In fact, you can kind of tell now that the line of reflection, which is hidden here, has to be somewhere in here. In fact, I can find out exactly where it is. Well, it's got to be right there, right there-ish, and then it's got to be right here-ish. That must be the line of reflection that's hidden from view right now. But if I throw in this checkbox R, what this shows you is sort of how things are happening, right? It's kind of like turning the page in a book. In other words, sort of I take this thing and I flop it over the other side. One of the things that helps you understand is how orientation is reversed in a reflection. Do you notice that? Going from A to B to C in the left hand, the blue image, pre-image, is reversed on the right hand side. As you go from A to B to C, now you're going counterclockwise, whereas you're clockwise on the left hand. So it's really like sort of taking something and flopping it upside down and viewing it, I guess, through sort of a transparent page. So here's the lines that connect A, B, and C, I guess, points and their images. And here's the line of reflection. And what nice thing here is that the line of reflection itself is able to be changed, right? So we could change it to right here. We could change it to right here. We could let the line of reflection be one of the points on the triangle. Ooh, my dynamic Reflection doesn't work then, but sort of nice way to play around and gain a real conceptual understanding of what's going on with reflection. Of course, when you when the line of reflection, seems like I broke the reflector thing, but when the line of reflection, when 2 points are on one side and 1 point's on the other side of the half plane, you get these intersecting triangles, and of course the points where they intersect here and here must be on the line of reflection itself, because those points are being mapped to themselves. So some really neat things that you can play around with in reflection in GeoGebra. So I'll let you play more with that on your own. Let's take a look at another one. We took a look at reflection. Let's do rotation next, why don't we? So here's what we have with the rotation. So in other words, we have a triangle that's being rotated by some angle, and it's being mapped to a new triangle. And of course, you should be able to change the triangle and see how that affects the rotation. By the way, this is an example of an animation, and there is a pause button right here if you want to pause it. The other thing I should tell you is that all of the transformations are grouped here on the, I guess it's the fourth drop down from the right. So there's reflection about a line. You can actually reflect about a point, but we won't talk about that in this course. You can also reflect in a circle, which is pretty neat to play with. But here's rotation, here's translation. You have to have a vector to do that, and here's dilation. So these three and that one at the top will be, of course, the things that we'll deal with in the course, talk about today. So I'll unpause it just because I kind of like seeing that. Well, what things do you think are hidden? This is one thing I didn't talk about, but of course the points in a reflection always travel along paths that are circles, which should sort of make sense, because if this is the center and I'm rotating everything by a certain point about that center, then everything is moving along concentric circles. And then of course there must be some angle of rotation. Right now I have the angle set to be 90, but this is dynamic too. So for example, if you want to rotate by 180, it would look like this. Or if you wanted to rotate by, say, 116.57 or some real small angle, it would look like that. So really a fun way to think about rotation, dynamic angle, and of course the tidal is the last thing. So some neat things to play with. Of course, the center D is also dynamic, so we should be able to sort of change everything according to what the center is. And placing the center, say, on a vertex is kind of interesting. The X is almost like a hinge. But there it is, rotation explained via GeoGebra. Let's take a look at one more. I'm going to go ahead and close. I guess I'll just minimize that. The last one is translation, which is sometimes called a slide. So in other words, we take the figure and we just slide it all a certain direction. And here are the lines. And I think this one, maybe it isn't controlled. I'm trying to remember how I controlled the, no, these are all, oh, there it is. So C prime is the, I guess, the vector of translation from C to C prime. You can control the slide by controlling C. But there's the idea. Everything moves the same distance in the same direction. So kind of interesting here, of course, is that these segments must all be congruent if everything's moving the same distance in the same direction. And of course, these lines that connect point and image must be parallel as well if everything's moving the same direction, the same distance. So that's what we see for translation. So some things you could discover by playing around with GeoGebra. Okay, let's go ahead and go ahead and do this last piece, which is let's create one that displays dilation and its properties. So here we go. This is the way it looks when I fire mine up. I think I'm going to get rid of the axes, but I think I will keep the grid for myself here. So I guess the first thing to investigate is what do we need for dilation? If you hover over the dilation tool, it says select an object, then a center point, and then enter a factor. So in other words, the scale factor can be entered um, uh, manually, and it'll stick to that scale factor even though you change, let's say, where the dilation center is and where the vertices of the figure are. But what might be interesting to introduce to you right now is this idea of a slider. Wouldn't it be nice if the factor itself was editable so that we could look at dilations other than, let's say, 2? So to do that, I'm going to introduce to you today this idea of a slider. And a slider is just a number that's placed on a little segment. So I'll pick the slider. It just says select a position. So I'm gonna put the slider down here to the right, and I'm gonna call this scale factor. I think it'll let me do that. You can have the slider be a number, an angle, an integer, or even a random number if you'd like. I don't know why you'd want that, but there it is. I'm going to let it start at 0 since a scale factor that's negative doesn't really seem to make much sense to me in this setting. And then let's let the maximum be, since I'm going to let it be 3 or something like that. And then the increment is how much you want the slider, how sensitive you want the slider to be. For example, you could make this 1 and it would be 0, 1, 2, or 3 is what you're choosing. But I'm going to make it a little bit more fine. I'm going to let the increment be 0.1 and hit OK. So now you can see that there's a number called scale. Looks like you can't name it with 2 words, but you can name it with 1 word. And scale ranges from 0 to 3, and there it is. So I'll let the scale be, let's let it be 2 to start with because we're kind of familiar with 2. And then what I'm going to do is I'm going to choose a polygon, and let's just do our friendly old 3, 4, 5 triangle that we had. Didn't quite get it, did I? Let's see. There it is. I'm going to go ahead and name these points. By the way, I have my options set. I have my options set for labeling to be no new objects. And if you want that always to be the case, all you have to do is save your settings. You know, when you make option choices here for font size or labeling or rounding, you hit save settings, then that will always be the case. You can always restore the default settings here if you want, but I've saved settings with labeling being no new objects. I just don't like all the labels, and so that means I have to bring labels in when I want them, but I like that better than erasing labels that I don't want. So I clicked on point, and then I'll do show label. There it is, A, B, and C pop up. And so that's nice. We have a triangle, A, B, and C. We want to use this dilate. So we have an object, but we don't have a center point. So I'll create a center point, and that one will also show label. There it is. So now I have everything I need to construct a dilation. I have an object, a center point, and a scale factor, and all of those should then be dynamic and be able to be changed once I dilate ABC. So let's go ahead and pick dilate ABC, and the order here is important. Shoot, sorry. I'll delete that. So the order is important. You have to select the object first, then the center point, and then enter the factor. Okay, so here we go. I'll pick dilation. I'm going to select the object, which is this triangle. So I think that'll get both sides and points and interior. And then I need to pick a center point, that's D, and then it says, what about a scale factor? I want it to be this scale. So I'm going to type in SCALE and hit OK. And there it is. There's my new dilated figure. And the neat part is, of course, that if I move this, then the dilated figure will move accordingly. If I put it on a corner, oh, that looks familiar. If I put it on a side, that looks exactly like what we got before. If I put it in the center, I think that's pretty close. Or is this the one I did? I think I did that one. So here we have an example of a dynamic version of what we did using pen and paper. And what's really neat about it, though, now is of course, we can change the scale factor. One thing that's kind of neat to do always is to put the scale factor down to 1. And of course, if it's 1, and then what are we doing? We're just scaling an object to itself. We get no change at all, right, in the object. So scale factor 1, you can kind of think of congruence being dilation with scale factor 1, right? But we could also go smaller, right? We could go half size. And so now what does it do? It brings it brings that distance from C to D to C to half that distance, which would be D to C prime. So that's kind of neat to see. This would be what we would call, instead of an enlargement, a compression, or I don't know what you call it when you shrink down, a shrink. But we can go as big as 3, you can see here, with the scale factor I've chosen, and see then a triangle that's produced by dilating by a factor of 3. I don't know about you, I think it's really powerful to see this in a dynamic sense. So I'll leave it at 2. And then, you should think about some of the things that you might want to add to the picture to make it really convincing and show the properties that you want. And perhaps not reveal them all. Maybe ask students, what do you notice about D, B, and B prime, and hope that they see that those things are collinear. So I'd probably use a ray here from D to B, a ray from D to A, and a ray from D to C. And indeed, those are all collinear. I don't know, the ray seems to be, they all seem to be a little bit, dense, so I'm going to use dotted lines just to sort of make it a little bit less distracting. So now if we sort of play around, you can see how that collinearity breaks out. I find that really convincing, that it is very true. We're always true that the center of dilation, a point in its image, all 3 of them are collinear. Probably don't want to show that off right away, so what I'm going to do is make a checkbox to show and hide some of that. So let's just say rays. And the objects I'm going to select are all of these rays, so I'll select that one, and that one, and hit apply. So now I have a nice checkbox that shows and hides one of the properties of dilation, which is that a point in its image and the center of dilation are collinear. What else? It'd be interesting maybe to see the angles, to impress upon students that that the 2 triangles are similar. Of course, we can change the triangles too. We haven't done any of that yet. That's kind of neat. So maybe the way to do this would be to just measure sides and measure angles of each of the triangles. So I'll get the angle tool. It's kind of nice if you use the angle tool and just click on a triangle, you get all the angles and all the angles here. Okay, so let's put a checkbox for angles maybe. And I'll select all of these angles. There they are, apply it. So now we have a checkbox that shows and hides angles, and of course all of these angles, the corresponding ones, are congruent or equal in measure. It might be kind of nice to move these into the middle a little bit, just so we can see them. And maybe the last thing to do would be to do distances of sides. So I'll do distances. I think no, it gives you the perimeter. So I'll do distance of side, side, and side, distance of a side, and a side, and maybe move them out where we can see them fairly well. And then put a checkbox in for sides. So these are all distances. I wonder where I find those. Let's see, I guess. So I guess we just have to pick these segments. This is interesting. I wonder if we're going to see the segments disappear when we do this. If they do, we can, okay, so there they are, the sides. Yes, so the segments do disappear. So one easy way around this then is just to add them back in once these are gone. I'll just do that now. So essentially we have those same sides added in twice to the drawing, but you can see now that their distances pop up and down like that. And might be kind of fun to, let's make this scale factor a little bit smaller, no, a little bigger. Change some colors if you'd like. I'm going to right click and sort of try to get this first triangle. Holding the control down now, I'm getting a couple more pieces. And I don't know, let's make this the blue one. Make this part blue as well. So I guess I have a blue triangle. This way you can talk about it in a classroom setting by referring to the color. Let's make this one a red triangle, I guess. Didn't get that one though, did I? And then the center, just make it red as well. There we go. Points, I could make these points red as well. There we go. We have something blue and red. You can definitely see the red triangle move when I move point D. Both triangles move when I move a point on A, B, or C. And I like it. I think it works pretty good. Sides come up and angles come up and down, and the rays come up and down. So it seems like a pretty good worksheet that might help students or a teacher in a classroom setting understand the properties of dilation. And that's really all I have for this week. Hope that the lecture gave you a good sense of transformational geometry and maybe a few tools for your classroom, as well as some instruction in how to represent these things with technology. Let me know if you have questions, and we'll talk to you soon.